In the heart of the heavily forested state of Maine, a groundbreaking story unfolds. The birth of the world's first bio-based 3D printed house. This innovative structure, poised to transform the future of construction, is the brainchild of Dr. Habib Dagher, a Lebanese-American professor who leads a cutting-edge research lab at the University of Maine. After years of research, the award-winning engineer has found a greener, faster, and more affordable way of building homes. Hi, I'm Namo Abdullah. In this program, I'll take you inside the challenges and triumphs of Dr. Dagher's team as they make history with their eco-friendly innovation.
It started with a message from the Maine Housing Authority, Maine State Housing, that said, we have a big crisis and we can't build enough homes. Can you help us print them? I'm originally Lebanese and came to the U.S. as a teenager. I came at 17 years old because of the civil war in Lebanon, and I thought I was going to be here for one semester for college, and here I am, over close to 45 some years later, still in the United States. So I have 2 master's degrees and a PhD, master's degrees in engineering mechanics and structural engineering, and a PhD in structural engineering as well. Came to UMaine and started the research center here, and the Advanced Structures and Composites Center, and we've grown from 5 people 27 years ago to 411 people today. We need in the U.S. over 8 million homes right now. In the state of Maine, we need close to 70,000 homes by 2030. We have a labor crisis. We don't have enough people to build homes.
3D printing, or additive manufacturing, is about creating objects by depositing materials layer by layer, following a digital model. For decades, it has been used to create prototypes, models, and parts for various industries. These days, it's also applied to construction with impressive results. I'm in Newport News, Virginia, where we are witnessing a groundbreaking project that could revolutionize the future of housing. Behind me are houses being built using 3D printing technology. These are a pair of houses being built as part of a partnership between Alquist, a U.S. pioneer of concrete 3D printing, and the non-profit organization Habitat for Humanity to 3D print affordable houses for low-income people in Virginia. These houses have been built with concrete, the most common material used in 3D printed houses. Concrete is durable and widely available, but not that environmentally friendly.
This house is 1,360 square feet, and from the time that we got the printer set up and started printing to the time we were finished the 3D portion, it was in between 35 and 40 hours of printing time.
How can we use technology to bring down the cost of housing, right? And especially in the current environment where costs of construction have just continued to rise and rise and rise globally, not just in the United States. We're seeing the need for technology as one way to try to bring down the cost of housing.
So in a nutshell, it's likened to what most common people know, like an icing bag that they use to decorate a cake. You take it and you squeeze the icing out to create a shape. Well, this is basically what is done. Except what you are squeezing out, or extruding, the correct word, is concrete. And it's a special mix of concrete. There's several different manufacturers that make the 3D printable concrete. It's got special properties to it, which allow it to harden, but yet still be flexible enough to print and bond as each layer gets done. Well, this particular printer is capable of printing any shape, anything imaginable that can be inputted into the machine, it can print it. Most people think that it puts everybody out of work, and it's not really the case. They kind of see, the printer and think, oh, that's, it's just one guy standing there running the printer, and everybody's out of work. But it's not really the case. It takes about 6 people at this point to man the site, because there's reinforcement that has to be added during the day. You have to load the mix into the hopper, the dry mix, and someone's got to run the printer. I think anybody could easily learn to 3D print. There's many people that use the home printers, and the technology for this printer is really no different.
There's challenges with the environment, right? If it's hot, if it's windy, right? If it's humid, these affect the print itself, right? So you can't just think of all those before you get out there. You have to, in some ways, get out there and try it and see what's happening, and then adjust.
Well, what is the optimal weather condition for this to work for?
Yeah, low humidity, 50 degrees. Which is the same. It's the optimal with concrete too. 60 degrees. So it's you don't have a lot of wind, right? It's allowed to cure at the rate that it wants to. It doesn't have all these environmental factors that are affecting the curing rate.
3D printing isn't just for small houses. It's making waves in big projects too. Take, for instance, this villa in China. It has been 3D printed. There are plans to 3D print a 21-acre hotel in Texas called El Casmico. This cutting-edge medical center in Thailand is also 3D printed. Over in Saudi Arabia, one of the world's tallest 3D printed houses is in Shams Al Riyadh. The 345 square meter structure is nearly 10 meters tall.
There was a UN publication, I think in 2016, about housing the world, right? The amount of housing that is required, that we need to produce, is so vast across the world. Predominantly, we use concrete across the world, right? Less so in the United States, but across the world. If we rely on that historic formula, there's just no way we can do it. And it's so environmentally, it can be so bad environmentally from a carbon standpoint with the cement, but also just the resources that go into making this. So we have to find other materials, and we're starting to see people working with that.
Aware of concrete's limitations and adverse impact on the climate, Dr. Dagher starts looking for alternative materials that are more flexible and eco-friendly.
Concrete is not the most environmentally friendly material. As you know, concrete production is a big contributor to climate change and climate change gases. So being able to use biomaterials that are developed to build homes is a way to reduce our carbon footprint significantly as a society. Our research center has a strategic plan, and it's called GEM. And it stands for Green Energy and Materials. So our mission is to bring green energy and materials to society.
Dr. Dagher knows that asking the right questions, not having all the answers, is what makes innovators. He has a list of questions for his 400-plus member team to answer.
Do we have materials that will withstand, that are strong enough to do this work? Do we have materials that meet the fire and toxicity requirements? Do we have materials that we can produce at a massive scale that allows us to make a dent in the housing crisis? So there's a variety of very challenging problems. But the technical problem in terms of how to produce these materials and how to print with them was a very, very challenging project. We tried a lot of different formulations of materials. We looked at the strength, we looked at the durability, we looked at the thermal expansion and contraction, and how compatible is that with existing material systems. So that was a major research effort that lasted a number of years to land on a formula for the material that actually works and does the job.
Franklin County, where we've learned the J mill will close early next year.
All good things must come to an end, right? Well, today was that end for one of the last standing parts of a Bucksport paper mill.
Dr. Dagher and his team realize the solution might be in their own backyard.
The state of Maine is the most heavily forested state in the United States. About 90% of the state of Maine is covered by forests. So the forest products industry is a big part of our economy. And we had 7 pulp and paper mills shut down in Maine over a few years. So that created a glut of biomaterials and biomass that otherwise used to go to the pulp and paper mills that have no place to go right now. To give you a sense of how big that is, it's about 1 million tons per year of material that has no place to go.
At Dr. Dagher's lab, 2 promising materials are identified to make the paste for the 3D printer to build houses: bioresin and wood fiber. Bioresin is a sticky substance derived from corn, while wood fiber is fine sawdust obtained from trees. Dr. Dagher's team used waste wood from defunct pulp and paper mills. There are 3 major reasons for choosing those specific materials. They are renewable and recyclable, reducing the environmental impact of construction. They're highly insulated and customizable. Unlike concrete, these materials allow for printing the house parts in different weather conditions, as the printer doesn't have to be on site.
So these pellets is what we feed our printers. And so the printer takes these pellets and they basically heat them and melt them and extrude them through a nozzle. And we would deposit those layers one by one. In concrete 3D printing, they're essentially taking the cement and the water and mixing it and depositing it layer by layer. What's different here is that in a concrete, you have to develop a concrete formulation that sets, but you can't print a horizontal surface. In our case, we're able to print horizontal surfaces with our material, so because it sets a lot faster, and we can print at an angle, at 45-degree angle, and that allows us to print 3-dimensional structures.
Does it harden faster when exposed to air than concrete, this material?
We've designed it to harden, yes, in anywhere between 1 and 5 minutes, depending on layer time. And so we design each layer that we deposit in such a way that when we come back, it's hardened enough, but still warm enough so you can have good adhesion between the layers.
Dr. Dagher's team is breaking new ground. They have no recipe to follow, only theories to test. They face challenges in their experiments.
Because nobody's ever done this before. You don't really know what you face. So yes, the challenges were many. This was not a rose-flowered road. It was a very difficult road, but we're a lot better at it now, and BioHome 3D 2.0 would even be done faster and be bigger. Of course, you're never certain that everything's going to work, but we had confidence that our team had enough experience to be able to address the challenges that we need to move forward with. At one point in time, the machine shut down. Everything shut down. And we went back to our equipment suppliers and worked with them, and nobody could figure out what was going on.
This is not Dr. Dagher's first challenging project. His legacy extends beyond 3D printed houses, from pioneering floating wind technology to receiving global recognition for bridge innovations. His work has made award-winning contributions to the field of civil engineering.
And floating wind technology is a major technology for the future of society, and we're the leader in the US in that particular field right now. 10 years ago, we deployed the first floating wind turbine off the US coast. It was built and designed in our laboratory.
According to his colleagues, Dr. Dagher is a leader who fosters a culture of teamwork, seeing it as essential for innovation.
Working with Dr. Dagher is like nothing else I've ever experienced, because he sees what people are capable of even when they don't. And that's why we're doing this interview in a house, in a 3D printed house made out of bio-based materials, because he knew that we could do these things. And I think it's so easy to always say, that's too hard or that's never been done. But working in this environment under Dr. Dagher, as well as with the University of Maine, it's the attitude of none of us is as smart as all of us, and we can do these things. If we all work together and we put our minds to it, we can do it.
Back at the construction site in Bangor, Maine, Dr. Dagher's team is troubleshooting what is believed to be the world's largest 3D printer.
So we had a very strong team. The team is very well experienced. We have, as I said, we have over 400 people who work in this laboratory, engineers and scientists and physicists and so on and so forth. Having such a varied team, we knew that we had the right people when the challenges came up to go out and solve them, and that turned out to be true. And it turned out that because we're processing so much material, the dust from the wood fibers, inside the pellets, accumulated on a valve that opens and closes the feed, the infeed to the extruder. And there was so much dust accumulated inside that the electronics for the valve weren't working anymore. But you could not have expected that when we started. And it was a simple way of basically putting a fan on that valve so we can keep the dust off of it.
With persistence, Dr. Dagher's team finishes the project. The state's governor and U.S. senators joined the inauguration ceremony in October last year.
And today we celebrate the first 3D printed house made entirely of bio-based materials, printed with wood flour. Now I'm sitting here thinking about Turkey Day coming up and making a gravy, and I'm thinking, wood flour, who'd have thunk? This home could eventually help meet the demand for new housing in Maine, sheltering people and providing homes, while also eliminating carbon emissions in the building process and supporting our traditional forest products industry. A true hat trick for Habib Dagher and his team. I'm proud that my Maine Jobs and Recovery Plan helped support this project with $15 million, federal money, thanks to Senator Collins.
Thank you so much, Habib. Habib has thanked everybody. Why don't we all thank Habib for his vision?
After the excitement surrounding the house's grand reception, a major question lingers about the small, charming abode crafted from wood fiber and corn resins. Can it withstand Maine's harsh winter, marked by heavy snowfall and icy temperatures?
We built it to find out if it does essentially do well in a very extreme environment. Well, we were concerned, for example, about expansion and contraction of this material, because it's a new material. When it heats and cools, it's going to expand and it's going to contract. Now, this house is a test prototype, and there's sensors around the house. If you look right in the middle of the ceiling there, you see a sensor. These sensors have been collecting data on the house, both structural data as well as environmental data and heating, cooling data.
After a year, the house has seen all the seasons. It's time to see how well it has done.
And it did extremely well over a year period. Of course, we found a few minor issues, but we can easily solve them. So this material you see right now, even though it's made with biopolymers and with wood fiber, is stronger than concrete in compression. Okay, yet it's 100% recyclable, and you can drill into it and cut into it. So it's a very unique material that can be used in a variety of places. But also having homes that are 100% recyclable is very important as well. So this house is 100% recyclable. To recycle this material, you can grind it and then print again with it. And we're doing that 5 times right now to see what happens to the properties of the materials in every cycle. And if this house is used for 200 years, for example, and you reuse the material 5 years, you're thinking about 1,000 years of recycling here that we're shooting for these material systems. But what's unique about this is there's cavities in the ceiling, in the walls, and in the floor. And we're able to incorporate a bio-insulative material in those cavities to provide the R values that's necessary. So when we printed this home, when you print concrete homes, you typically just print the walls. When you print, you've seen that, they actually pour a foundation as you normally would, and then print the walls, and then come back and build the roof trusses and the rest of the house manually. In this case, we didn't do that. We printed everything. We printed the floor, we printed the walls, we printed the roof, all in one piece.
We now have the world's largest thermoplastic 3D printer, and we use that to print things like houses and boats. And we realized we need bigger, we need more, because if we want to do this at scale, we have to do it faster, and we have to do it with a larger throughput of materials coming through the printer.
We're breaking ground this summer with what we call the factory of the future. It's a factory to scale up the production. Of course, the faster you can produce these homes, the lower the costs are going to be. This house is designed in modules, right? And our goal here is to be able to build one of these in about 48 hours. Okay, 2 days essentially, using one machine. The material costs roughly are about $40,000 for this house. A typical 600 square foot home in our state of Maine of this size costs close to $300,000. So, but the materials here are about $40,000. Now we're evaluating what the production costs are, and once we have those numbers, we believe that we're going to be very competitive. So starting this year, this coming year, we're going to produce BioHome 3D 2.0, which is a bigger version of this at much higher throughput speeds. So, and we have interest from a number of developers to develop developments with this home. One of those developers is called Penquis in this area, and we have an agreement with them to produce a 9-home neighborhood using this technology. People say, "Wow, I didn't expect it to look so nice, and I could live in this." Okay, and that's really what matters at the end, is do people really like this? Do they want this? So of course, all of us as researchers love to see it come together. From an engineering perspective, was a major engineering feat. But seeing people react to it so positively has been very, very, very rewarding to the entire team.